Next we are going to discuss the systems which have a time delay. So how will be a time delay model? Time delay is nothing but if a signal is starting from 0, let us say. Then if there is a t0 seconds delay, then it will start after t0 seconds. Right? That's all, nothing else. So in the transfer function, how will you model this time delay? When a function f of s is given, if there is a time delay, then it will simply become e to the power minus s t naught. That's all. So now for our case, let us consider a minimum phase. Since the open loop transfer functions are mostly minimum phase, we will mostly discuss minimum phase systems only. Okay. So consider a minimum phase system with time delay TD, let us say. Okay, time delay. So how will we represent this? G of s into h of s we can write as g1 of s into h1 of s, that is the original system without time delay, into e to the power minus s t d. This you can write the original system without time delay. Now if you substitute s is equal to j omega, what will you get? G of j omega into h of j omega is equal to g1 of j omega into h1 of j omega into e to the power minus j omega t d. Now what will be the magnitude of gh? This will be same as the magnitude of g1 h1. So there is no change in the magnitude because of the time delay, because the magnitude of a phasor function will be unity. So no change in magnitude because of time delay function. Okay, but what about the phase? You can see that the phase gh will be the initial phase minus omega t d. So all of the points now will be rotated by an amount omega t d. For example, if you take the Nyquist plot of the polar plot of g1 h1, let us say it is like this. Okay, then what will happen to the plot of gh? That means including the time delay, this is going to start at the same point, because when omega is equal to 0, the phase will be simply equal to g1 h1. So the initial phase will be same, but as frequency increases, the amount of phase shift will keep increasing. Okay, and finally it is going to be something like this. It is going to spiral multiple times before finally becoming 0. So this is the plot of g1 h1 into e to the power minus j omega t d. In this case, how will you decide the stability? So we will be concerned with the first intersection. This decides the stability. The first intersection, since there are multiple intersections, we are talking about the first intersection. Okay, first intersection decides stability. In the same manner, if the intersection is towards the right, then it is a stable system. If it is towards the left, then it is an unstable system. So you can write here, if the first intersection is to the right of minus 1, 0, then it is a stable system. Otherwise, it is unstable. So you can see an example here for various time delays. So let us say the point minus 1, 0 is here. Let us take one function like this. Okay, and another function, let us say it is going through like this. So let us say the time delay here is t d1 and this is t d2. You can see that this system is unstable because the intersection is towards the left, whereas this system is stable. Now what is the relation between the time delays td2 and td1? Which one is higher? TD2 will be higher than TD1, because for a system we see that minus omega TD is the phase difference when there is a time delay. Okay, as TD becomes higher, the phase shift also becomes higher. Okay, so TD2 will be greater than TD1. So what is the most important conclusion here? Greater the time delay, less stable the system becomes, right? Because as we keep moving towards minus 1 comma 0, then the system stability is considered to be reducing. Another way in which we can decide the stability of a time delay function is by using a critical trajectory. So till now we have been dealing with a critical point. What is the point? Minus 1 comma 0. Now we are going to deal with a critical trajectory. So we will see what is that. So we know that g of j omega into h of j omega, we can write a pure time delay function. We can write as g1 of j omega into h1 of j omega into e to the power minus j omega t d. Now when will this system be on the verge of stability, instability, or verge of stability? Both are same. It will be when the first intersection is passing through minus 1 comma 0, right? So if this point is minus 1 comma 0, then the system is considered to be on the verge of instability. Okay, so we will see what is this, when will that instability, verge of instability condition occur. That will be the critical trajectory. That's how you're going to get the critical trajectory. Okay, so how will we do that? G of j omega into h of j omega will equal minus 1 plus j 0, right? Because this is the real part and this is the imaginary part. Now minus 1 comma 0 means the real part is minus 1, imaginary part is 0. So we write as minus 1 plus j 0. When this function is equal to this, then it is said to be on the verge of instability. Okay, so this is what g1 of j omega into h1 of j omega e to the power minus j omega td is equal to minus 1. So that means g1 of j omega into h1 of j omega is equal to minus e to the power plus j omega t d. Okay, so now this function, this is the critical trajectory. So how when you draw this on the plane, the real and imaginary parts of the function. So now we want to plot this minus e to the power plus j omega td. What is the magnitude? Magnitude is going to be simply 1, right? Because the magnitude of phasor is 1. Then what about the phase? The phase is going to be, if it was simply e to the power j omega td, it would have been omega td. But since we have minus, it is going to be 180 plus omega td. So this you can find from expanding this function. So when you expand it, what will you get? Minus e to the power plus j omega td is going to be minus of cos omega td plus j sin omega td. Now when will both the functions be 0? In the third quadrant. So that means you will write cos 180 plus omega td, which is minus cos omega td, plus j sin 180 plus omega td. So this will give you what? E to the power j 180 plus omega td. So the phase is 180 plus omega td. Now using this information we can get the polar plot. So when you substitute omega is equal to 0, the magnitude will always be 1. So when the magnitude is not changing, it means that it is a circle with center as the origin. So you can first draw the circle of unit magnitude. So this is going to be minus 1. This is going to be 1 plus j0. This is 1 minus 1 plus j0. Okay. Similarly, this is going to be 0 minus j0. This is 0 plus j0. Then what about the value of omega? That means at this point what is omega? At this point what is omega? Right? So we know that when you substitute omega is equal to 0 here, you are getting the phase to be 180. So that means this is the omega is equal to 0 point. So instead of omega we will take omega TD. So this is equal to 0. When omega TD becomes equal to pi by 2, then this angle will become 270 degrees. So this will be 270 degrees. Then again this is omega TD is equal to pi. Here omega TD is equal to pi plus pi by 2, which is 3 pi by 2, and it will again continue. Here it is going to be 2 pi and then 4 pi. Here pi by 2 plus 2 pi and so on. Here pi plus 2 pi, which is 3 pi, 5 pi and so on. Okay. So now this is the critical trajectory that we are talking about. Okay. So you can write trajectory of minus e to the power plus j omega TD. Now what we do is we take the plot of G1 into H1 and we will see where it is intersecting the critical trajectory. That is how you are going to get the stability. For example, let us once again draw the critical trajectory. So let us say this is the critical trajectory. Now if the function G1 H1 function is intersecting it in the third quadrant. Okay, so you can see here that this point here is minus 1 comma 0. So this system should be stable. So when the G1 H1 function intersects the critical trajectory in the third quadrant, then the system is said to be stable. Then what about this? When it is intersecting the critical trajectory at the real axis itself, then it is called at the verge of instability, right? So you can write here, this is stable, this is verge of instability. Okay. Then what about when the intersection is beyond the real axis, that means in the second quadrant, then it is called as an unstable system. Okay, so this is how you decide the stability based on critical trajectory. If these are what? G1 H1 plot. Okay, if the G1 H1 plot intersects critical trajectory in second quadrant, then it means that the system is unstable. If it intersects on the negative real axis, then the system is said to be on the verge of instability. And if it intersects in the third quadrant, then it is a stable system. Finally, one last point is, how do you find the critical time delay? That means if you have a function which is much stable, okay, about point minus 1 comma 0 is here and G1 H1 is like this. This is the initial system or the original system. Now you are inducing a time delay of, let us say, TD. Then it is going to be shifted like this. Okay. If you include another furthermore time delay, then it is going to be at the verge of instability. Okay. So this is TD1, this is TD2, let us say. You are inducing time delays to the original system, which is G1 H1. Then how much time delay you can introduce before the system becomes unstable? That is the critical time delay that we are talking about. So here what is the critical time delay? TD2 is the critical time delay. So you can write TD2 is the maximum time delay which can be introduced to the original system without making it unstable. So we need to know what is this maximum time delay, right? Beyond that, we should not introduce that time delay. So what is that? How do you find it? It is quite simple actually. what will be the function? G1 of j omega into H1 of j omega into e to the power minus j omega Td critical, we will call it, okay, TdC. So this should be equal to minus 1. If you consider the phase, then the phase of G1 H1 minus omega TdC is equal to minus 180 degrees. So from here you are going to get omega TdC is equal to the phase of G1 H1 plus 180 degrees. So now you have two unknowns here. What is that? Omega and TdC. So the omega, how you will find out? You will find out from the magnitude condition. This is the phase condition that we have taken. Now using the magnitude condition, we have G1 of j omega into H1 of j omega is equal to 1, because the phasor here magnitude will be simply 1. So from here you can find out omega. Okay. So this is equation 2, you can write. Find omega from equation 2 and then find critical time delay from equation 1.